Okay. Oh yeah, and on top of all that, I have a cold, so hopefully the whole sniffling sound won't be bothering you guys too much. Okay, so chapter 4. You have moved on now in your organic chemistry experience. No longer are you reviewing / getting into organic chemistry. We are now in the middle of it. We're going to talk about alkanes, right? We're going to talk about why molecules that are carbon and hydrogen look different. You know, what makes some molecules more active in your body than others. You know, we're going to learn a whole lot of ways to communicate about chemistry and chemicals, specifically alkanes and cycloalkanes, because they're honestly not the most exciting molecules. We burn them for our cars, right? We have gasoline. That's octane. That's an alkane. But besides that, there's not a lot we can do except learn how to communicate effectively about organic chemistry and learn why, or set the foundation for more complex organic chemistry that we start with the alkanes and the cycloalkanes. So I guess to start with, I've said this word a bunch, and if you haven't looked at your book, hopefully you have, but if you haven't looked at your book, you might be wondering what an alkane is. An alkane in bond line form looks like something like this, where you just have, 3 carbons with 3 hydrogens, 2 hydrogens on this one, 3 on this one, and that's the whole molecule. That's an alkane. We've talked about these a little bit in the earlier sections, and they have a few cousins. They have an alkene. It's a common name for something that has a CC double bond in it that is not conjugated. One of the reasons for starting this chapter in the way that the book has is that you really need an appreciation for why we talk about molecules in a certain way. You know, and this is the point where if I had slides, we would talk about organic chemistry as a foreign language and trying to think about how to name molecules. Just like we had the question before the test about what is an amine, you know, this a lot of systematic naming that we came up with, which we'll go over in a second. But these are alkenes here, and there's a closely related second cousin, the alkynes that have CC triple bonds. And alkynes and alkenes both exist either with or without conjugation, but often we talk about them if they're in less conjugated systems. And then, just for fun, we'll throw in one cycle at this point, a fully conjugated fully conjugated C6 molecule called benzene. And this is a pretty big one in organic chemistry. If you ever look up like chemistry memes or something, you'll see people talk about hexagons all the time. And this is primarily the hexagon we'll be dealing with in organic 232. There's another hexagon we'll deal with in this class a lot more often, especially for this test, and that is what's called cyclohexane, so named because it's a cycle of hexane 1, 2, 3, 4, 5, 6. Right, so chemistry didn't used to be like this, where there was so much information about organic chemistry, where 100 people could come together who are just like taking a whole bunch of different studies and learn about organic chemistry. It used to be, you know, you would have a professor who was interested in organic chemistry, and they would toil away in their weird dungeon laboratory, and they would have a whole bunch of weird smells, and they would look more like alchemists than anything, whatever you're thinking in your mind of an alchemist. And at the end of the day, maybe they find a molecule. You know, they discover some new linkage pattern of organic chemistry, and they decide, this is fantastic, I'm going to call it some name that they give it arbitrarily, whatever they're thinking in their head. There are some really good ones that are in the book, some fantastic examples of this. Probably my favorite that they have is this bioactive molecule that's used a lot in medicines. Get the structure exactly right. Yeah, there we are. Okay, this molecule is pretty cool. It's like two amides and a dicarbonyl on the bottom. And the chemist who came up with this was so happy, he named it after the best woman in his life, whose name was Barbara. And we call it barbituric acid. That's a real story. This happened all the time in chemistry like 100 years ago. And you can see how that would get very confusing. You know, this is barbituric acid. If you had some other chemists who were working on fertilizers and they were working with a lot of urine, they found out that this molecule was responsible, one of the molecules responsible for the smell and the good properties of what they were doing with urine, whatever that was. And they call this urea because it came from urine. There's no system to this. It's all just confusing and honestly very hard to connect with, especially if you're trying to learn about the chemistry. So some really smart people came together about, I don't know, 100 and some odd years ago, maybe 120, I think so. Yeah, 1892. There we go. It's in your book. And what they did was they met in Geneva because a lot of good accords and negotiations happened there. And they decided that we need this whole set of rules. We need a set of systematic rules so that if we talk about a molecule, we can talk about it, and every single time, you and I can both know what it is that we're dealing with. You know, we can know if the molecule has a very convoluted structure or if it's a very simple structure that happens to make piecemeal weird, right? But we need a system because there's too many of us who want to learn about organic chemistry. So these rules, called now the IUPAC rules, I'll just write it, it's not really a big deal, but IUPAC rules. These rules basically give us a framework so that if I tell you we are working with 2-methylbutane, you can draw that every time because you know what 2-methylbutane is. It's just like how in English we have a set of grammar. And we have rules for how we talk to each other, and we have ways that we construct sentences that make sense. This is the exact same thing we're doing in chemistry. And this general type, I mean, I've said it a couple times, but the overall type of naming system it is the IUPAC rules, but the overall system, what am I trying to say? This is called systematic naming. It's not a chemistry term. It's just a term for when you decide to do this with a set of rules. You say, we need to categorize these things, and there's a set of rules for it. So now you follow the rules. That's a system. You name things with the system. So it's all fine and good to say, oh, we have a system that's in place. It works. You can now name any chemical. But the question is, for you guys, since you'll be tested on this in a few weeks, how do you name any chemical? Like, for instance, let's say I gave you something, or you saw something drawn on a piece of paper, and that thing looked like this. Yeah, I'll just do it this way. How could you name this molecule drawn in bond line drawing formula, bond line drawing, and be able to name it such that your partner working with you or some person 1,000 miles away can know exactly what this molecule is? And luckily, because it is a systematic naming system, systematic way to name chemicals. There are just a couple rules we can follow, and as long as we do that, then you should be able to name them every time, easy peasy. So the first thing you do, hopefully if you've read your book, you already know exactly what you do, is you find the longest uninterrupted chain of carbons. This gives you an idea of what is called the parent chain. So here, hopefully you can see, and you'll get faster at it the more you do it, is that we have 1, 2, 3, 4, 5, 6, 7, 8 carbons that make up the longest chain. Does everybody see that? 8 carbons. So that means the parent chain is an octane. Again, if I had my cool OChem as a foreign language thing, we would go into a whole deal about parent chains and A&E and where that word comes from, but we're not going to today. I'm going to just tell you that A&E, ane, is how you both say that it is an alkane, because alkane also ends in A&E, but also you specify specifically, which is the best way to specify something, that the parent chain, or that this oct group, 8 carbons, is the parent chain. Right, so let's just, I'll just kind of circle this, outline it, so you can see later. Oop, went the wrong way. There we go. Cool. It kind of looks like a dragon or dinosaur or something now, doesn't it? Okay, so maybe you've noticed that I use something now that we haven't talked about before, and that is the 3-letter prefix in front of ane. These come from, I think, Latin origins, these ways to number chemical positions that we have in organic chemistry, and it's something that you will need to memorize. You will need to say, oh, I have 1 carbon, that's a methane. Oh, I have 2, that's eth. 3 is prop. 4 is bute. 5 is pent. 6 is hex. 7 is hept. 8, oct. 9, non. And 10, dec. You will need to be able to count to 10 using this formalism without really having to think about it too much. And it's going to make your lives a lot easier. It's not too much memorization, but it will be very important, and I think it'll be super clear that it's very important as we go through these chapters. It's not much. It's only 10. You know, you can name up to 100 in the system, but we're only going to do 10. So please do that. Right. So we now have our longest parent chain. Here, 8 carbons. That is an octane. What if the carbons, I'll do it in red because we all know this by red. What if the carbons were instead, can I do it? Yeah, I bet I can. Oh, I already messed it up. See, there we go. Yeah, that feels better. We all know this shape, right? We see it like a few times a day, at least if we drive. This 8 carbon ring. Now, instead of being octane, this 8 carbon ring would be what? Yeah, cyclooctane. Now you see, hopefully you see also that in reading your book, I'm putting some dashes in there that shouldn't be there. I'm doing that for you in this moment as we go through it because it's easier to see them broken up. Normally, when you name these things, you just say cyclooctane with no dashes. But I'm just splitting up the prefixes and the suffix so you can see what the words are made of. All right, so back to our funny dragon chemical guy. Maybe. Does anybody still drawing this? No? Yes? We're good. Okay. Back to this guy. Let's redraw him. All right. He looks less like a dragon now. Okay, so we have our parent chain. I'm just going to draw in the carbons here. That way you can see that's the parent chain. But what's the next step? That only tells us a few things. It doesn't tell us everything about the molecule yet, right? Now we need to know what is coming off of this parent chain, because you can see there are other carbons here that are coming off that we haven't dealt with. So now these are what's called substituents. Another foreign language concept in organic chemistry are what's called substituents. And we are going to talk about this word a lot. Substituents is the name for something that is related to something else. Okay? Very vague definition. In organic chemistry, we are going to use it in such a way that it means anything attached to the thing you are talking about. So that means if you have a carbon, its substituents are whatever is coming off. It doesn't matter what they are. These things here, those are substituents. It's just a word you're going to have to memorize, and just remember that it means stuff coming off of the thing you're talking about. And in this case of naming the substituents off the parent chain, the best thing to do is first identify what the substituents are. And we can do that fairly easily by just circling the substituents coming off of the carbons labeled in the parent chain. Right? So I've circled in blue the substituents from the main parent chain. Does everybody see where now that comes from? Okay. So now it's good if we name the substituents. You found the parent chain, you have identified the substituents, now you should name them. So in naming them, this has 1 carbon, this has 2, that has 2, and this has 1. So we go back to our really fun naming convention here. 1 is a methyl. Ooh, that's a new suffix. Ooh. YL. This is another chemistry language moment, and il means a substituent. It just means that that thing is attached to something else. It's a shorthand way of showing that in writing. So the one with 2 is ethil. Same up here, ethil. And up here, this 1, that's a methyl. All right, so if you're following along at home, we have found the parent chain. We have identified if there are any substituents, and we have named them. So now what we need to do is find a way to put all these things together, this information, such a way that we can effectively communicate what this molecule is. But there's a problem. You know, when you moved here to start studying, you had to find some place to live, right? And each of you were probably given a post box that somebody visits every day and maybe drops off some mail or something. And that is a physical address. Well, right now, in our molecule, we have no physical addresses for where these substituents are. How do you say where they are located on the parent chain? How do they do it on the street? You start from low numbers and you go to higher until you find some other street or something, right? So why don't we just do that here? We're going to number from one side to the other 1 to 8, because it's octane, 8 carbons. And this is a big deal for learning naming, is remembering how to do the numbering. Because if you don't get the numbering right, the name doesn't make sense. It's just like how you were trying to give somebody directions to your house. If you don't give them the right address, they can't find your house. So what the trick is with the numbering, you always want to make the numbers as low as possible for whatever it is you're talking about in the molecule. So that means here we have two options. I'm going to do them in two different colors here. Starting on the left, I'll do 1, 2, 3, 4, 5, 6, 7, 8. All right. And then maybe I shouldn't redraw it. Is it getting a little too crowded? Maybe it is. Let's just redraw this guy here. Yeah, that feels better. There we go. Okay. Redo that. On top, we have left to right numbering system because all the carbons are here, if you remember. So on the bottom, let's do right to left numbering system. All right. So our goal is to reduce the overall total number of every substituent. So that means that we have to fun lights. There we go. Okay. Now we're back. Hopefully you can all see your papers again. So essentially what this means is if you have something in the middle, the type of naming that you choose, left to right or right to left, probably isn't going to affect its, this, double. That's a new one. There we go. I'm learning all kinds of new tricks now. Hopefully it stays that way. Otherwise, I'll have to take another 10 seconds and fix it. If it's in the middle, obviously changing which way it's numbered, left to right or right to left, isn't going to make a big difference. But if it's closer to the ends, you can imagine how changing the way you number this molecule is going to make a huge difference. Because if you start left to right, this guy's going to be number 3, this one number 4, 5, and 6. But if you start right to left, you have 3, 4, 5, and 6. Yeah, I know what you're all thinking. This is a bad example of numbering. Exactly. Because in this molecule, because they're all 3, 4, 5, and 6, it's not going to matter really which way you start, right? However, I will draw one that it does matter. There we are. Okay, in this molecule, it has 1, 2, 3, 4, 5, 6, 7, which makes it a heptane, right? And it has 3 substituents, right? They're all methyls. So if I do the same numbering system, one on top, one on bottom, left to right, 1, 2, 3, 4, 5, 6, 7, and on bottom, 1, 2, 3, 4, 5, 6, 7. Now, hopefully you see that there is some difference in the naming. Because if you go left to right, that third methyl would be number 5. But if you go right to left, that third methyl is number 3. And that matters because in this particular example that I drew for this purpose, both the other methyls are 2 and 6, no matter what. So in this way, you will have 2 blank 6 trimethyl heptane. And we want the lowest number, so we're going to call this methyl 3 instead of 5. Does that make sense? I'm seeing some head nodding, so that's a good sign. Good. 2, 3, 6. So coming back up to our poorly designed example, now we have 3, 4, 5, 6. Let's just go ahead and name this all together, because we can do it, and I think it will be a good segue into the next part of naming, that's important. So this molecule up top with all the numbers, very cluttered, is 3,6-dimethyl four, 5-diethyl. Oh, I messed that up already. Look at me. Good, this is a teachable moment. 4,5-diethyl octane. There we go. Okay, so I messed that naming up. Can anybody tell me what I did wrong? Yes. That's right. Diethyl should be first because when you are writing down substituents before the parent, so let me go a little slower. When you're writing down substituents before the parent, octane, if you can read that, you have to do alphabetical naming. And if you don't, then the name is wrong. So if this were my homework and the point was to name this molecule correctly, I did not do that. The other thing you might notice is that numbers can never go beside letters. They have to have a dash. Anytime you have a number, just put a dash, put a letter. Or put a dash before the next letter. You saw that in the example above as well, the one I did correctly. Trimethylheptane, you have a dash after the numbers and before the letters. Now, yeah, alphabetical naming system, commas in between the numbers as well. One last thing, because like I said, I'm trying to go through this a little faster, just because I wasn't here Tuesday. The last thing I will talk about is what's called complex substituents. And complex substituents are ones that don't have a simple name. Okay? So if I were to show you this molecule, this is C3,4H3,6,9,10, C4H10, right? In this molecule, you have 3 carbons that are the parent and 1 substituent, right? That's a methyl. That's pretty easy. But what if I gave you this one? Oh, well, there we go. Now it makes sense. So this poorly drawn molecule is 1, 2, 3, 4, 5, 6. That's hexane, right? Because that's the longest parent chain. We have 1 substituent here. The common name for this, like I talked about, the common name for this is isopropyl. Like when you use Purell and it has isopropyl alcohol, that is this substituent, isopropyl. Isopropyl. And IUPAC rules say there are some common names that you can use just because they're so pervasive in modern day chemistry, they kind of just kept those in. However, I would say and suggest to you guys that it's probably better for you not to worry about common names. You can use them, and that's fine. I know what they mean because I use them a lot as well. But if instead of calling this isopropyl, you called this 1-methyl ethyl, I could deal with that because that would also be a correct naming system. So this would be the 1-methyl, and that would be the ethyl group there. Yeah, exactly. So in this case, yeah, sorry. Yes, that's right. And in this case, I didn't do it again. No, I did it right, I think. Because if you do, there's 1, 2, 3, 4, 5 coming off the other side. This side? 1, 2, 3, 4, 5? The other side. 1, 2, 3, 4, 5. Oh, look at that. See how this is not an easy thing. This is why we need systematic naming, and coming up with something off the cuff is not so easy. Yeah, in fact, in my notes, I thought about that, and I made it one chain longer. So let's call this instead. Is that right? Yeah, that seems right. Yeah, heptane instead. Yeah. See, sorry about that, guys. To try to find the exact perfect example for each one is not so easy. Yes. One methyl ethyl, right? Because in this case, the ethyl group. I'll redraw it here. Okay. So imagine that it is attached to something up here, right? So in this case, this substituent, we would call this the ethyl group parent chain, and then its substituent was a methyl. And the methyl is attached to the first carbon in the ethyl group, so then it would be 1-methyl ethyl as a group by itself. And then when you go to name this molecule that now has the right linkage pattern, because it's heptane instead of hexane, you would call this, let's see, 1, 2, 3, 4, 1, 2, 3, 4, 4, 1-methyl ethyl heptane. You use the exact same rules. You just stick that whole complex substituent in where the normal substituent would be. All right, it gets better from there, because the whole point of this system is to be able to name more and more complex stuff, right?